So what we wanted to show here is the entire pipeline for an autonomous vehicle. In this first phase here, we have a vehicle that we added 6 cameras to. We have front fisheye cameras, we have a narrow field of view, other fisheye cameras, and a standard rear narrow field of view camera as well. In addition, there are 4 laser scanners on board that we're collecting data from. So here's a view of actually just the raw data collection coming into the car. And again, it's a full 3D representation. In this case, I can spin around and view it from different angles. We never show this to the driver, but this is an example, again, of the massive amount of data coming into the vehicle. And from that, we're able to actually use the video information and use a structure from motion algorithm to define points in 3-dimensional space and couple that with the LiDAR information of the other vehicles that we have. From that, we're able to extract a lot of information about what's happening around our vehicle, so we can essentially detect other vehicles and be able to actually classify what those vehicles are. So using our deep neural network, we're able to in real time identify all the vehicles in the scene and understand more about what those vehicles are. In fact, we do this because different kinds of vehicles have different driving characteristics, and there may be some vehicles that, such as an ambulance or a police car, that will need to be able to detect and pull over in emergency situations. So the next phase, once we've detected all those objects, we need to localize our position. So we have GPS on the vehicle, but we're working with here using their HD maps, and we correlate what we're seeing, what are the lane boundaries, what are the road boundaries, with the known HD map, compare that to the live information we have, and then we can localize to make sure we're driving in the correct lane. And we can also then adjust our path and potential paths based on the curvature of the road and the other vehicles. So here we can see these red potential lines are not valid paths, but once the car is moved out of the way, there's a valid path there. And again, we can visualize this from all different directions. And finally, what we do is we put it all together. We can see an overlay of all the data, all the different vehicles that are moving, the dynamics, and what the potential paths are that we can take. And if we were to get cut off, by having the ability to understand what is around us, we could take evasive action as well. Now, the key thing here is that this is all what's going on inside the brain of the self-driving car. This is running on the Drive PX2 in the vehicle in real time. This data, though, is too complex to display to the driver. So what we need to do is have a connection from a Drive PX autopilot computer into our Drive CX cockpit computer that's actually driving the displays inside the vehicle. And so from that, let's walk over to the final station and take a look at that. A critical part of building trust in the autonomous car is being able to communicate to the driver and passengers of the vehicle, as well as then make sure that other vehicles understand the intent and the behavior of the autonomous car. In this example now, what we've done is we've taken all the massive amount of data, the trillions of operations per second that are going on inside the Drive PX2, and now we're visualizing in the cockpit what the driver could possibly see. And if you notice now, we're projecting the driver's windshield view up above, but you can see on the cockpit vehicles entering the scene before they actually become visible to the driver out the windshield. So this technique essentially allows us to eliminate mirrors in the vehicle. We can get a full 360 surround of the vehicle, and so it gives the driver the confidence that the autonomous car is sensing the world around it. And then also we can communicate to the driver what the intent of the self-driving car is, so they're not surprised if we're going to change lanes, if we're going to exit, if we're going to take some form of evasive action because of a potential hazard. That information will be communicated to the occupants of the car. Another key thing, of course, is that we need to be able to drive like a human, not like a computer. So it needs to be smooth lane changes, smooth exits, smooth curves, smooth acceleration, smooth braking. And we use deep learning as well to anticipate behaviors of other cars to be able to then adjust our driving behavior to be very safe.